Yes,
Okay, so in this second example, so in the first example, you did a GW calculation to get the quasi-particle band structure of silicon. And in the second example, then we'll look at what happens when you include electron-hole correlations and how we can get the optical absorption spectrum also of silicon using something called the beta-salpeter equation within BerkeleyGW. So as you saw in the introductory talks, in order to calculate well, I guess not in the introductory talks here, but in order to calculate optical absorption spectrum of a material, you need to solve the beta-salpeter equation. And so we're going to do this within BerkeleyGW. And the BSE part of the BerkeleyGW code gives you optical absorption spectra that are in good agreement with experiment for a wide range of materials, from bulk semiconductors like silicon to two-dimensional semiconductors like molybdenum disulfide, and also bulk and two-dimensional metals like graphene. So I'd like to emphasize here that solving the beta-salpeter equation is really necessary to give you qualitatively correct optical absorption spectra. Because if you look at this optical absorption spectrum for silicon here, the black dotted line is the spectrum from experiment. And then this blue solid line is what you would get if you, at the GW level, if you neglect the electron-hole interactions. And you can see it doesn't agree with experiment even at the qualitative level. But after you include the electron-hole interactions through the beta-salpeter equation, then you get this red solid line here, and you see excellent agreement with experiment. So it's really necessary to do this in order to get qualitatively correct optical absorption spectrum. So in this talk, we're going to address how to perform practical BSE calculations using BerkeleyGW. We'll start by having a brief theoretical and methodological overview. Then we'll take a look at a typical workflow for doing a BSE calculation in BerkeleyGW. And then we'll go over some technical issues that are unique to the BSE code. So first, theoretical and methodological overview. So optical absorption is really this two-particle process because you have a photon coming in here and it excites an electron into the conduction band, and that electron leaves behind a hole in the valence band. And so if you think about this process within the GWRPA, or independent particle picture, then you just have this transition from this hole state, Vk plus Q, to this electron state, CK. And you can calculate the optical absorption spectra using Fermi's golden rule. And the optical absorption spectra, which is the imaginary part of epsilon, just goes as this matrix element between this valence state at Vk plus Q and the conduction state, Ck. And you have a delta function that corresponds to the energy of this transition. However, in a real material, you don't just have the electron and the hole. The negatively charged electron and the positively charged hole can interact and give you a correlated state known as an exciton. So this electron and hole form a correlated state known as an exciton. And instead of this single transition from a single K point in the valence band to a single K point in the conduction band, you can then think of the exciton as a linear combination of transitions between the valence band and the conduction band, as illustrated here. And you can write the exciton state as this linear combination of some whole wave functions and some electron wave functions with an amplitude that's described by this coefficient A of VCK. So this exciton is, you can think of it as a particle and that's excited from the ground state. And then depending on the strength of the electron-hole interaction, you can get any number of bound states, which are represented by these black lines here. And then there's also a continuum of free electron hole pairs. And the onset of the free electron hole pair, in the onset of the continuum is going to correspond to the quasi-particle band gap. So then the excitation energy of your exciton is going to be the energy at which the exciton is excited. And then the binding energy of the exciton is the difference between the excitation energy and the quasi-particle continuum. So if you write the beta-salpeter equation in a basis of electron hole pairs, you can write it in this effective Hamiltonian form, where you have the BSE Hamiltonian, and then the eigensolutions are your exciton wave functions psi s, and the eigenvalues are your exciton excitation energies omega s. And then in the basis of electron hole pairs, the BSE matrix looks like this. On the diagonal of the matrix corresponds to the transition energies between the valence states at Vk and the conduction states Ck. And then you have this sort of behaves like a kinetic energy term. And then you have this interaction kernel K, which describes the electron hole interaction. So the interaction kernel is made up of two interactions. You have the direct Coulomb interaction between the electron and the hole, which is an attractive Coulomb interaction that's mediated by the screened Coulomb interaction. And then you have an exchange term, which is repulsive and is mediated by the bare Coulomb interaction. When you solve the beta-salpeter equation, what you do is you first construct this kernel, and then you construct the BSE matrix, then you diagonalize this matrix to get your exciton wave functions and excitation energies. And then you can calculate the absorption spectrum from Fermi's golden rule, and this tells you that the absorption spectrum, or the imaginary part of epsilon, is proportional to this matrix element between the ground state 0 and the exciton state S. So this is just a very broad theoretical overview of what it means when we solve the beta-salpeter equation. So now let's dig into some details of this solution. And here I want to emphasize again that solving the beta-salpeter equation gives you these very dramatic qualitative differences in the spectrum. And this is true even if the exciton binding energy is quite small. So you can determine the exciton binding energy, remember, is the difference between the excitation energy and the quasi-particle band gap. And you can also determine it by looking at the difference between the onset of the interacting and non-interacting spectra. So between the onset of the red and blue lines. And from this, you can see in silicon, the exciton binding energy is actually quite small, only about 15 millielectron volts. But even this small exciton binding energy is enough to give you these very dramatic qualitative changes in the optical absorption spectrum. So when solving the BSE, there's one major technical issue, which is that the quasi-particle corrections and the kernel matrix elements need to be calculated on an extremely fine K-point grid. For instance, you need 300 by 300 K-points to converge MOS2. So this becomes, if you want to solve this, if you want to calculate this BSE matrix on this very fine grid, it quickly becomes quite computationally challenging. So instead, what we do is because it's expensive, matrix elements, so the matrix elements of this interaction kernel and the BSE on this very fine grid. So here, V and C are indices of the valence and conduction bands, and KFI is an index, as a K-point index on a fine K-point grid. So we don't want to explicitly calculate all of these matrix elements on a fine grid. So instead, what we do is we calculate these kernel matrix elements on a coarse grid and then interpolate to a much finer grid. And within BerkeleyGW, we use a method for this interpolation called projection interpolation. And what we do is we explicitly generate coarse and fine grid wave functions at the DFT level. So when you go through this example, you'll be asked or you'll be provided with DFT wave functions on a uniform coarse K-grid and on a uniform fine K-grid. And then we expand the fine grid wave functions in terms of the coarse grid wave functions. So we treat the coarse grid wave functions as some complete basis that we can use to expand the fine grid wave functions. So with this method, because we explicitly have the wave functions on both the coarse and the fine grid from DFT, there is no need to perform Wannier interpolation, and this allows us to capture band crossings correctly, and as well as other features of the wave function character, because we explicitly have these wave functions. So to do this interpolation, the first step is to obtain the wave functions on a coarse grid and a fine grid. And then we expand the fine wave functions in terms of coarse wave functions. So essentially, U here is the periodic part of the block wave functions. And so we say that U on the fine grid, UK fine, is equal to some linear combination of U on the coarse grid with some coefficient. And this coefficient C is just the overlap of U on the fine grid with U on the coarse grid. And once we obtain these coefficients, we then interpolate the quasi-particle energies, which we also calculate on a coarse grid, which was done in the sigma step of your last example. Sorry, I seem to be, okay, one of my equations has gone missing here. But we interpolate the BSE kernel matrix elements, also using these coefficients. So essentially here, what we're doing is we're expanding each of these. On the right-hand side, you have the kernel matrix element in terms of the wave functions on the coarse grid. And then we multiply by these expansion coefficients so that the kernel matrix element on the left-hand side, which on the fine grid, is equal to some linear combination of kernel matrix elements on the coarse grid. So in essence, what we're doing is, because we need very fine K points and we don't want to calculate the kernel for all of these K points. Instead, what we do is we calculate the kernel for fewer K points and a larger number of bands, and then use that to interpolate to more K points and a fewer number of bands. So in practice, we're trading bands for K points. So if we were to try to calculate the kernel matrix elements on a fine grid just from brute force, it would look something like this. We would just explicitly calculate for a small number of bands. We'd explicitly calculate a large number of K points. But we don't want to do that. Instead, what we do in BerkeleyGW is we explicitly calculate a small number of K points and a large number of bands. And so the blue dots in this figure, and we use those to interpolate the kernel matrix elements to a large number of K points on a small number of bands, which are the yellow dots here. So in order to get a good interpolation, what we need to do is include a large number of bands from the coarse grid and start from a coarse grid that's not too coarse. So we'll get in later, we'll talk later about what that means. But how do we know if we include enough bands? So we can figure out if we've included enough bands from the completeness relation, which tells us that the square of all the coefficients, C, should add up to 1. So that's the error in our interpolation is essentially how much this sum of the squares of our coefficients deviates from 1. So In the code, when it does this interpolation, it's going to report what all of these errors are, or how close we are to achieving this completeness relation. And these are going to be printed into these two output files, dvmatnorm.dat and dcmatnorm.dat, where dvmatnorm.dat tells you how good the interpolation is for the valence bands, and dcmatnorm.dat tells you how good the interpolation is for the conduction bands. Another place that these values are reported is in absorption.out and int eqp.out. So in these two output files, it'll give you a warning if any of the errors is greater than 5%. So next, let's take a look at what a typical workflow in BerkeleyGW looks like. So this BSE calculation in BerkeleyGW has the following steps. First, in step 0 is basically what we did in the last example. We're going to calculate the quasi-particle corrected band structure on a coarse grid. So there we need the dielectric matrix, which we got from epsilon, which is called epsmat.h5. And then we also need the quasi-particle energy, the GW quasi-particle energies, which we calculated from sigma on our coarse grid. Then the first step of the actual BSE calculation is going to be to calculate the BSE kernel grid that corresponds to our epsmat file and our quasi-particle energies. So we're going to refer to this as k-coarse for the coarse kernel. And this is done by the executable kernel.x in BerkeleyGW. And in the second step, we're going to run an executable called absorption.x. And what this executable does is it's going to take as an input file this kernel from this, which is referred to as BSE mat, and then it's going to interpolate this kernel from a coarse grid to a fine grid and construct the full BSE Hamiltonian. So the kernel, which is the kernel plus the diagonal term. And then once it's constructed the full BSE Hamiltonian on the fine grid, then it's going to diagonalize the BSE Hamiltonian. And this will give us the eigenvalues and eigenvectors of the Hamiltonian, which can be then used to construct the absorption, the optical absorption from Fermi's golden rule. So now let's dig a little bit deeper into what is done in each of these steps. So in step 1, remember we're using kernel.x to calculate the BSE kernel. And this is quite a time-consuming step, which is why we want to do it on the coarse grid. Because computing these kernel matrix elements, so these are matrix elements between an electron hole pair at one k point and a different electron hole pair at another k point. So the size of the matrix is going to go as the number of valence bands times the number of conduction bands times the number of k points squared. So this is quite an expensive calculation. And it's going to be calculating these two interactions here, the exchange interaction involving the Baer-Coulomb interaction and the screened interaction, the direct interaction involving the screened Coulomb interaction. And both of these are stored as separate matrices within this output file, which bsemat.h5. And so to get to this screened direct term, you need the dielectric matrix you calculated in the epsilon step. And for most bulk systems, it's recommended that you use the same wave function for the kernel step that you used for sigma and for epsilon. So the same k-grid, so which allows you to reuse the dielectric matrix that you generated previously. And this wave function is referenced under the name WFN_CO for coarse wave function. So then once you have this BSE mat, So in order to generate this, when you run kernel, the code reads an input file called kernel.inp, and there are a number of flags in this input file. One of these flags is the number of valence bands and the number of conduction bands. So this is basically the number of valence bands and conduction bands that you want to use to interpolate the coarse grid to the fine grid. So you should use a larger number of bands than you actually think you'll need here in this step. And then another flag is you can either use symmetries coarse grid or no symmetries coarse grid. So this tells you whether or not the code should unfold the wave function using symmetries. And so typically, in order to save a computational cost, you do want to use symmetries in your wave function in this step. And then the same as for the GW calculation, you need to let the code know what kind of material you have. So if it's a screening underscore semiconductor or screening underscore metallic, in order to let the code know what the correct behavior is as in the long wavelength limit. So the one key thing to remember is that the number of bands you should use in the kernel calculation should always be more than what you think you'll need for absorption because of interpolation. So the next step is then to do the absorption calculation. In the first part of the absorption calculation, you're going to be interpolating from a fine K-grid, from a coarse K-grid to a fine K-grid to build the BSE Hamiltonian, and then diagonalizing the BSE Hamiltonian. So as input, absorption is going to need to have access to the same WFN underscore CO that you used in kernel. And then eventually, absorption is going to calculate the imaginary part of the dielectric function using Fermi's golden rule. So if you expand this expression, so you have this matrix element, this velocity matrix element from the ground state to your exciton state S. And if you expand your exciton state in terms of the electron hole basis, then you see that you get this sum over the the electron hole coefficients A multiplied by a matrix element describing this transition from a valence state at Vk plus Q to a conduction state at Ck. And so what is this Q in here? So this Q, because this is the velocity matrix element, this Q actually corresponds to the momentum that's of light that's transferred to your exciton. So for optical absorption, of course, the momentum of light is very small, close to zero. So we're just going to use an arbitrary, very small Q for this Q here. And typically we use a value that's 10 to the negative third. So then we need to know the valence states at this K plus this very small Q, and the conduction states at K. So to do that, again, we're going to use two different wave functions. So we have a wave function on a uniform fine K grid called WFN fine, from which we're going to read the conduction states, CK. And then we're going to have another wave function file called WFNQ underscore fine to read the valence states at K plus Q. And this WFNQ fine is on a uniform K grid that's been shifted by a very small Q vector, which is close to 0.001. And finally, the direction of this Q vector is also going to determine the polarization of your incoming light. So if you want to change the polarization of your light, you can change this small Q shift for WFN, the direction of this small Q shift for WFNQ underscore fine. There's another technical detail, which is that if you want to converge the density of states, you can use, for WFN fine, you can either use a gamma-centered grid K-grid with no shift, or you can use a grid with some random shift. And if you look at the density of states, what you'll find is that if you use a random shift, you're effectively using more K points because you're avoiding symmetry equivalent high symmetry K points. So this random shift is going to give you a much smoother density of states, and the density of states will converge much more quickly with your K-grid if you use a random shift. So we always recommend that you introduce a random shift to the K-grid for WFN underscore FI. So that leads us to how we set up the input file for absorption. So here, this is what the input file will look like. And it asks you for to define 4 bands. Oops. So first, it asks you to tell to say how many bands you used on the coarse grid for both the valence and the conduction states, and this should be the same as for the kernel calculation. And then it asks for how many bands you want on the fine grid, and so this should be a smaller number than the number of bands you used on the coarse grid. And these are the bands that you're going to interpolate to and that the BSE matrix is actually going to be constructed for. Then it asks you, so here in absorption, then you have 3 wave functions. You have your coarse wave function, your fine wave function, and your fine wave function with a small Q shift. So you have to tell the code whether or not you're going to use symmetries for them. So again, if you used symmetries for the coarse wave function in kernel, you should do that again in absorption. And if you've randomly shifted the fine wave function, then you should not use symmetries to unfold those K points for both the fine grid and the shifted grid. And then another important flag is that, so diagonalizing the BSE matrix gives you some eigenvalues. And then to get the absorption spectrum, essentially what you do is you place you have a line at each eigenvalue, and then this line has some broadening. And this is where we define the broadening. So you can tell the code to use a Gaussian broadening, and this energy resolution gives you the size of the broadening in electron volts. And then finally, so the diagonal part of the BSE matrix is the electron hole transition energies, and we want to use the GW transition energies there. So we're going to, so this flag EQP underscore course corrections tells the code to read the GW corrections, the GW quasi-particle energies that were calculated in sigma on the coarse grid, so, and interpolate that to the fine grid and use that for the diagonal of the BSE matrix. So finally, I'm just going to briefly discuss a few other technical issues unique to the BSE code. So we have a lot more parameters in BSE, and so we need to converge those, and then we'll look at how we can analyze our results and some other features of the code. So for the BSE calculation, there are 4 additional convergence parameters that you have to consider. One is the number of K points on their fine grid. The other is the number of bands in the fine grid, and the number of K points on the coarse grid, and the number of bands on the coarse grid. So essentially what you need to do is you need to increase these values until the final observable that you're looking for, such as the optical absorption spectrum, converges. Here are just some rules of thumb for this convergence. Generally, the number of bands on the fine grid is going to correspond to the energy window of interest plus the exciton binding energy. So for instance, if you're interested in the optical absorption spectrum up to 3 electron volts, then you need to include all of the bands in your band structure that involve transitions up to 3 electron volts. So this is pretty straightforward. Then the number of bands included on your coarse grid needs to be a larger number in order to get a good interpolation. And you can estimate this from int eqp.x and from and from the error estimates that the code gives you while doing the interpolation. And then in order for the K points on the course grid, usually for a typical bulk material, you can use the same K grid that you used for sigma.x. So really the only thing that's, for a typical bulk material, the only thing that's tricky to converge is the K points on the fine grid, where you just have to increase the number of K points until your exciton energies converge. Then in BerkeleyGW, we have a number of tools to analyze the results. So the optical spectrum is reported. So we report both the imaginary part of the dielectric function and the real part of the dielectric function, epsilon1. And these are reported in these two output files. The first output file is absorption underscore no EH.dat. This gives you the optical spectrum without electron hole interactions. And so this is what's called the GW RPA level. And then the second output file, absorption underscore EH.dat, gives you the optical spectrum, including the electron hole interactions at the GW BSE level. Another useful output file to look at is eigenvalues.dat. And so this reports the eigenvalues of the BSE matrix, which corresponds to the excitation energies of all of your excitons. And so this is useful to look at. You can open it up, take a look at what the actual excitation energies are, see if there are any degenerate excitons or dark excitons that don't show up in your absorption spectrum. And then finally, we have a utility called summarize eigenvectors.x, which tells you where the eigenvector is coming from, so where the exciton is coming from. So is this exciton composed of bands in a specific region of K-space, and does it come from a specific subset of bands? So in order to run, summarize eigenvectors.x, we need to make sure that we print out the eigenvectors of the BSE matrix, which are the exciton wave functions. And to do that, this is not done by default in the code, because sometimes, depending on your system size, the number of eigenvectors you have is quite large. But you can tell the code to print them out by including the flag write underscore eigenvectors in your absorption.input file. And then there are also some other features in the code that are good to know about. So one is what I described previously. So we do an explicit diagonalization of the BSE matrix to get the eigenvalues and eigenvectors. But you can also, that gives you a lot of information about the excitons, but it tends to be, depending on your matrix size, it can be very expensive. If it's too expensive to do this explicit diagonalization, instead you can use the Haydock or Lencho's methods implemented in the code, which uses an iterative solution for the absorption spectrum, gives you the absorption spectrum, but no eigenvectors can be obtained. Another option is to, in our interpolation by default, to get valence bands, we do the expansion over valence bands on the course grid, and to get conduction bands, we do the expansion over conduction bands on the course grid. But you can also use an unrestricted interpolation where you expand over both the conduction and valence states. And this is something that's very important to do for metals. And then finally, what I showed you before is we calculate the optical absorption spectrum using this velocity operator, V. Instead of the velocity operator, you can use a different operator called the momentum operator. And this allows you to not use a shifted WFNQ find file. However, the results it gives you are less accurate because it neglects the non-local part of the pseudopotential. Finally, we have, by default, the code uses something called the Tamm-Dankhoff approximation, but this is also optional. You can You can turn it off if you want. And by default, the code assumes that the screening of the electron hole interaction is static. So these are the two major approximations used when we solve the beta-salpeter equation. So in summary, the beta-salpeter equation needs to be solved on a fine k-point grid. In order to do that, we use BerkeleyGW to interpolate the wave functions from a coarse grid onto a fine grid. And as a consequence, we need to include more bands in the kernel step of the calculation. In order to do the BSE, we have 5 input wave functions. We have WFN coarse, which is your wave function on the coarse grid, which is used by both kernel and absorption. And then we have WFN fine, which is the fine wave function with a random k-shift, and then WFNQ fine, which is the fine wave function with a random k-shift and a small q-shift, which describes the polarization of the light. And these 3 wave functions are used by the absorption code. And when we do this, the BSE calculation, we have 4 convergence parameters: the bands on the coarse grid and fine grid, and the k-points on the coarse grid and fine grid. So then up to this in this morning's session, what you did is you use the epsilon and sigma codes to find the quasi-particle energies at the GW level, and these are reported in EQP1.dat. So you generated EPSMAT and EPS0MAT and EQP1.dat. And in the next steps, what we're going to do is we're going to take we're going to generate a coarse wave function and a fine wave function. Then we're going to run kernel, which takes as input the coarse wave function, EPSMAT and EPS0MAT, to build the kernel matrix, which is called BSE-MAT. Then we're going to send BSE-MAT as input into absorption, along with EPSMAT, EPS0MAT, the quasi-particle energies, and the fine wave functions in order to obtain the absorption spectrum. The final output will be absorption_EH.dat. So in this hands-on session, what you're going to need to do is to copy the second example from the project directory into your Scratch directory, and then again, follow the directions in the README files. And the final goal is that you will produce this absorption spectrum for silicon that you see on the left. And if you have time, you can do a partial convergence study of the k-point sampling and the number of bands. So any questions? So then I guess we can probably get started with the next session.
Yep, thank you, Diana. So yeah, we're going to go into breakout sessions again, and we'll have discussion with our instructors, including any general questions you may have from this too. And then right at the very end, I'll bring everybody back in here just for a moment to give you a closing thought. Okay, so I'm turning off